Look at 3, 4, 5, 6, and 7 on worksheet number 7 here, starting with question number 3. 3, we have a vector diagram. We know it's a good vector diagram because it's drawn head to tail here, as is number 4, as is number 5. Vector diagrams have to be drawn head to tail. What do we call this? This line that connects the start to the finish? We call it R, the resultant vector. It is the sum of the vectors. If I say 10 plus 20, it doesn't equal 30. 10 plus 20 equals R, whatever that works out to be. And theta, because displacement's a vector, we have to include direction. Our direction is given by an angle, and this angle is always measured from the start of your vector diagram. Okay, sometimes people look at it and say, well, where do I draw the angle? Like, is it here or is it here? Okay, it's in the first spot, because we always draw the angle at the start of the vector diagram. Now, some people are going to look at this as well and say, well, that's drawn tail to tail, right? I can't do that. Yes, you can. You can't draw the vectors you're adding tail to tail. The 10 and the 20 that we're adding together have to be drawn head to tail. But there's no reason why we can't do the resultant vector tail to tail and head to head. All right, so let's solve for R now. How are we going to solve for R in this right angle triangle? Somebody said a squared plus b squared equals c squared. That's called what? The Pythagorean Theorem. So we're going to say, well, it's going to look a little bit different than you do it in math, right? A squared plus b squared equals c squared. If we rearrange that, c is equal to the square root of a squared plus b squared. I'm going to say R is c, which is equal to the square root of 20 squared plus 10 squared. Now let's do that on our calculator here. Let's say square root of bracket 20 squared plus 10 squared, and that bracket gives me a value of 22.3607 meters. We're going to round that to 2 digits, or 22 meters. So there's the magnitude of my resultant vector. Now I'm going to solve for theta. Theta is, which trait function do I use? X is the adjacent, Y is the opposite. Opposite and adjacent go with tan. Now in math class you learn it's like tan is Y over X, right? I would prefer opposite over adjacent. You guys learn that? Y over X? If you don't know what I'm talking about, that's okay. How many people have learned opposite over adjacent? Good, I like that way better. Because it's not always y over x, depends on where your angle is. Okay, it's always opposite over adjacent. This is the inverse tan, second function tan of opposite, which is 10, over adjacent, which is 20. Now, we haven't used our calculator yet for angles today. We're about to, so the first thing we should do before we do that is sine 90. Make sure we're still in degree mode. We are. So now let's say theta is the second function tan, or inverse tan, of 10 divided by 20. Gives me a value of 26.5 degrees, or we'll round that to 26 degrees. Now, I mentioned to you yesterday that we really should express that relative to something, okay, relative to a certain frame of reference, but we'll worry about that later on, okay? Right now, let's just focus on solving for that angle. Good? Let's do number 4 as well. 4 involves a resultant vector right here from start to finish. Where am I going to draw my angle? Position 1, position 2, or position 3? 1, 2, 3. 3. Yeah, always draw it at the start of your vector diagram. R is going to be found by taking the square root of 15 squared plus 10 squared. Okay, let's do that. Square root of bracket 15 squared plus 10 squared gives me 18. So the magnitude of my resultant vector is 18. In other words, when I add 15 plus 10 together, I get 18 at a certain angle. And the angle is going to be found by, once again, the inverse tan function. Theta is equal to the inverse tan of opposite over adjacent. What's the opposite side here? Is the opposite side 15 or 10? Alex, is the opposite side of this triangle 15 or 10? 10. Good. The opposite side is the one that's not touching the angle, so it's going to be 10. The adjacent side is 15. So we're going to say the inverse tan, second function tan. I don't need to do my check again, right? Like, nobody's reset my calculator in the last minute since I checked it the last time. So I'm good for the rest of the class today without checking the sine 90 thing. The inverse tan of 10 divided by 15 gives me 34 degrees. And again, by rights, that should be expressed relative to something, but that's going to come later on for us. Okay, we want to focus on just getting the angle first, and then we'll worry about relative to what. Good? Number 5, similar, like real similar question here, right? Again, 10 meters to the west, 5 meters down, head to tail, that's good. The resultant vector is drawn from start to finish. It's not going to be drawn head to tail, that's fine. It's only the vectors that you're adding that need to be head to tail. What's 10 plus 5? 15? No. In this case, it's not 15. 10 plus 5 is going to be found by taking the square root of 5 squared plus 10 squared. Second function, square root, bracket 5 squared plus 10 squared equals 11. But we're not done, right? Because we haven't found an angle. Just like in those questions on day 2 of Physics 20, when you were solving for displacement in one dimension and you needed a direction, we need a direction here as well. The angle is found by the inverse tan function of opposite over adjacent. What's opposite here? So Anna, what's opposite? Is it 5 or 10? Good. 5, and then adjacent is 10, of course. So theta is going to be equal to, let's figure this out, second function tan of 5 divided by 10 gives me 27 degrees. Relative to something, but, oh, you know what? I didn't even draw the angle in, right? I should have. So Anna noticed that correctly noticed which side was opposite and adjacent, and I didn't even have the angle drawn there. Should be there, right? Always draw it at the start. Good there? Okay, let's take a look at 6 and 7. These ones are a little bit harder, not a great deal. But if you remember, the goal is always what? The goal in these problems is always what? Get a right angle triangle. In questions 3, 4, and 5, I had a right angle triangle. Do I have a right angle triangle here in number 6? No. Is that a vector diagram? Absolutely it is. Absolutely it is. Head to tail, head to tail. Okay, the resultant vector is drawn from start to finish. Absolutely it is. But I got to get a right angle triangle in order to use the Pythagorean theorem on this. So let's do that. How do we do it? How do we do it? Well, this is where we start doing our x's and y's. What's the x component of the first vector? How much, Jesse, how much of that 10 meters is x component? 10. How much of it's y component? Okay. Good. How much of that 5, that second one, is x component? Haley, how much of that second one is x component? 0. Good. How much of it's y? 5 meters. Good. Then how much of that 15 is x? 15. Good. And how much of it's y? 0. Good. Now let's add these up. 10 plus 0 plus 15 is 25. 0 plus 5 plus 0 is 5. And now we need to redraw it. How did I know to redraw that 25 to the right? Well, first of all, it's x component, right? And it's positive, so it's to the right. How did I know to draw that 5 up? Yep, because what? Yeah, it's y component and it's positive, right, Blake? Now my result, by the way, is that a vector diagram? It's drawn head to tail, right? That's fine. The resultant vector is drawn from start to finish. Look at the resultant vector that we have now versus the one that we had just a minute ago. What's the difference? The resultant is the same, right? But now it's easier to find because we have a right angle triangle. Now it's just like question 4. R is the square root of 25 squared plus 5 squared. Second function, square root bracket 25 squared plus 5 squared. Oh, look at that. Interesting. It rounds to 25. Is that okay? Yep, that's what it is. So it's okay. Theta is the inverse tan function of opposite over adjacent. Martin, what's the opposite side of the triangle here? Is it 25 or 5? 5. So it's inverse tan of 5 over 25. Do you expect to get a big number for angle here or a small number? Yeah, it's going to be small because we went over a lot more than we went up. We're going to say inverse tan, second function tan of 5 divided by 25 gives me 11 degrees. Relative to something, but again, we'll worry about that later on. And finally, number 7, hardest one yet. 1, 2, 3, 4 vectors, resultant vectors from start to finish. Is that okay? Is that a vector diagram? Everything's drawn head to tail except the resultant, which is drawn from start to finish, tail to tail, head to head. We got to do x's and y's here. Let's go in order here. The x component of the 8. The x component of the 8, Rochelle? 0. The y component is? -8. Good. Whew. -8 because it's down, right? The x component of the 12. The x component of the 12. What's that one, Blake? 12. The y component is? Good. The 10, the x component is, John? Yep. No. 0. And the y component is? Good. Carissa, the x component of the 4 is? Good. -4. And the y component is? Good. Add these up. This is 8. This one is 2. Now we redraw it. What have I done here? My resultant is wrong, isn't it? Yeah, what's wrong with it, Nick? Yeah, it's backwards, right? I didn't draw it from start to finish. I drew it from finish to start. It should be this way, right? So I'm going to redraw this now. 8 over 2 up. 8 over to the right because it's positive. 2 up because it's positive. My resultant vector I'm going to draw right here, which looks pretty much like my resultant vector there. It's not always going to be perfect because you're not always going to draw your vector diagram to scale, to a perfect scale without a ruler, right? But it should be very close. And now we can find this, find the value of r easily. Square root of 8 squared plus 2 squared. What is that? Is it 9? 8? Who has that? Is it 8.2, 8.24? So we're going to round that to 2 digits, 8.2 meters. And theta, where am I going to label theta? Position 1, 2, or 3? 1, 2, 3. Position 2, yeah, is the inverse tan of opposite over adjacent. Who's French math here? Okay, Jesse, what's the opposite side of the triangle? The 8 of the 2. 2, good. And the adjacent side is, of course, the 8, right? So we're going to say inverse tan of 2 over 8 gives me 14. Now, I asked that question, like, who's French math? You're allowed to do it any way that works, right? I just want you to at least be exposed to this and to understand this, and then you can make your choice. Okay, then you can make your choice. Let's have a look at this one now. This one is going to combine what we've just done with the last 3 questions on that worksheet with what we were doing yesterday before that, and that is vector components of angled ones, right? 30 degrees we see right here. Okay, we see a vector diagram right here, right? We see vector 1, vector 2, vector 3. They're all drawn head to tail, so that's good. It's legit. Our resultant vector is drawn from start to finish. That's fine. Our goal is to get a right angle triangle. So what we're going to do to get that right angle triangle is to add up all the x components, add up all the y components, and then redraw it as a right angle triangle. But my problem here is we have what I call a funny angle. If it's not 90 degrees or 0 degrees, it's a funny angle. 30 degrees is a funny angle. 45 degrees is a funny angle. 62 degrees is a funny angle. 88 degrees is a funny angle. And guess what? Guess what? Whenever you see a funny angle that is not 90 degrees, not 0 degrees, I want you to repeat 5 words. Got it? 5 words. Repeat after me. I don't like funny angles. Okay, repeat it. Wait. I don't like funny angles. I don't like funny angles. I don't like funny angles. Okay, let's get rid of them then. If you don't like funny angles, then let's get rid of them. Let's get rid of them the way that we did yesterday, right, which is using sine and cos. So here's what I'm going to do. I'm going to take this 15-meter vector. Let's just deal with it off to the side here, okay? This vector right here that's at a funny angle. Draw it over here to the side. It's 15 meters. We got 30 degrees labeled down here. Let's label this as the x component and this as the y component. Is this ringing a bell? We've done this, right? We've done this, just not as part of the bigger problem. Now let's find the value of x. What side of the triangle is x? Opposite, adjacent, or hypotenuse? It's adjacent, and we have the hypotenuse of 15. So what goes with adjacent and hypotenuse? Which trig function? Remember, so, ka, toa? Adjacent and hypotenuse, it's ka, so it's cosine. Cosine 30 degrees is equal to x over 15, adjacent over hypotenuse. Let's figure out what that is. 15 cosine 30 gives me a value of 12.9904. Now let's find the y component. The y component is the opposite side. We have the hypotenuse, so let's say sine 30 degrees is equal to opposite y over 15, which is the hypotenuse. And we've got 7.5 meters is the y component. Got it? Now what I want you to do is just draw a little box around this. Box it off. The reason I want you to box it off, not because it's critical, like it's not really critical that you do that, but the reason I want you to do it is because that's what makes this question different than the last 3 questions we worked on. The questions, was it 5, 6, and 7 on your worksheet that we went over. Otherwise, it's exactly the same. So we just box off, take off to the side, box off what makes it different. Now, remember, we just got rid of the 15. We don't like funny angles. The 15 was at a funny angle. We just got rid of it. It's dead to us. The 15 is dead to us. We never want to see or use that 15 again. So here's what I'm going to do. I'm going to replace the 15 with 12.99 and 7.5. And then I'm just going to, well, scratch that out. Why don't I want to see that number 15 and 30 degrees? Because it's dead to us. That's why. Look at what I got. It's not a right angle triangle, is it? But it looks an awful lot like questions 5, 6, and 7 now, doesn't it? Now that I've gotten rid of the 15 meters at 30 degrees, it looks virtually identical to questions 5, 6, and 7 on that worksheet that you did. So the key here is get rid of a funny angle. Make it look like questions 5, 6, and 7, which aren't really that hard. Now let's do our thing. What's the x component? What's the x component of the 10 meters? What's the x component of the 10 meters? 10. What's the y component of that 10 meters? 0. What's the x component of that 5 meters? 0. What's the y component of that 5 meters? Negative 5. Good. What's the x component of the 15? 12.99. What's the y component of the 15? 7.5. We're never going to say 15 again, right? Why? Because it's dead to us. One time I asked the question, we saw the funny angle. I said to my class, I said, what do you think when you see this funny angle? And everybody said, I don't like funny angles. And then I said, so what do? Somebody says, kill it. It's a little extreme, okay, but the point is not invalid. We want to get rid of it, right? That 15 meters is gone. Like once we've resolved it into x and y, it's gone, completely gone. Now let's add them up. 10 plus 12.99 is 22.9904. There's the total x. Negative 5 plus 7.5 is 2.5. There's the total y. Now I'm going to say 22.9904 to the right because it's positive, and 2.5 up because it's positive. And then I'll draw my resultant vector. And my resultant vector, a little bit of a different scale here, but you can see it looks pretty much like the first one does, right? Label it R. Where am I going to label theta? Position 1, 2, or 3? Position 1, yeah. Hey, we can do this now, right? Using Pythagorean Theorem and tan or sine law or whatever it is that you like to do. We got the square root of 22.9904 squared plus 2.5 squared. 23.1. We're actually going to round that to 23, right? And theta is the inverse tan function of 2.5 over 22. We're going to get a big angle here or a small angle? Yeah, I'm expecting a pretty small angle, right? What is it, 9904? 6 degrees. That's a little bit bigger than I thought it would be, actually. 6 degrees relative to something that we'll worry about later on. Did I hear somebody say that's so much work? Yeah, it is, isn't it? It is. Just wait. Wait till I give you a question with like 7 funny angles. Well, the good news is I won't. Although I could, right? I could, and it wouldn't be any harder. It would be a lot more work, but it wouldn't be any harder because if you can do 1, you can do 7 of them, right? The funny angles that I would give you on a quiz or a test would be 2 funny angles, because man, if you can do 2 of them, you can do any number of them. Make sense? What makes this different? Do you guys all understand 5, 6, 7 on that worksheet? Yeah? What makes this different? Funny angle. We see a funny angle 30 degrees. What do we say? I don't like funny angles. In fact, I like funny angles so little that I have a water bottle that says I don't like funny angles. So we take it off to the side, we get rid of it, we break it into x and y's, and then we just pretend that 15 never existed. You know what it is? You know what it is? It's like that brother-in-law in the family that nobody ever really liked. Then there was this nasty divorce. You got all these family pictures with that brother-in-law in it, and then you just kind of Photoshop that brother-in-law out like he never existed. Okay? That's the 15 meters right there. Photoshop never existed. Never existed. Okay? 12.99 and 7.5. That's the way it should have started in the first place. Okay? Got it? Okay. Let's take a look at your worksheet again now. I'd like you to work on, at your desks, at your worksheet, at your desk, please. Worksheet number 7. This time, let's go with questions 8 and 9. We might get to 10, but let's focus on 8 and 9 right now, okay? Let's have a look at number 8. What do you see in number 8 that kind of strikes you? This is a vector diagram, right? Head to tail. It's all good, right? I can draw my resultant vector from start to finish, right? No problem. What do you see in this one that strikes you? I don't know about you, but I see a 30-degree angle, and when I see a 30-degree angle, what do I say? I don't like funny angles, so I take it off to the side. I get rid of it. Let's take the 30 degrees off to the side. Let's get rid of it. There's my angle, 30 degrees. It's the hypotenuse there is 40. This is going to be x. This is going to be y. You'll almost always see me draw x in blue and y in green, color coding it like that. It's not critical that you do that, right? If you do it in one color, that's okay, but it just helps to kind of keep it straight for me. So I usually end up doing that. Okay, let's find the value of x. What side of the triangle is x there? Gabby, is x opposite or adjacent? X is next to the angle. It's beside the angle, so it's adjacent, yeah? Adjacent and hypotenuse, Miguel, look up here, okay? Goes with cosine. What does that equal? 33 point, what is that, 40 cos 30? Somebody's got to have that? 34.64. And then we'll find the y component, which is, well, that's going to be sine function, opposite over hypotenuse. This one's easy. 40 sine 30 is just 20. And then box it off. Why do I box it off? Because, well, it makes it, the rest of the question is the same as questions 5, 6, and 7 that we did. Now, here's what I like to do. I like to draw in 34.64. And I like to draw in the 20 meters right here. And then I like to just Photoshop out that 40 meters that, as far as we're concerned, never existed. And now, well, it looks like I got a right angle triangle. I don't really quite, because it's kind of cheating with 3 vectors there, right? But I'm gonna turn it into one. For my x component, I'm going to say 80. For my y component, 0. For my x component, I'm going to say 34.64. For my y component, I'm going to say negative 20. So we're going to add those up. And we're going to redraw it, 114. And 20. And lo and behold, look at this. The resultant vector looks the same, doesn't it? As it should, if I drew it to scale. Where am I going to draw my angle? Position 1, 2, or 3? 1, 2, 3. 2, yeah, at the start of the diagram. What's R equal there? I'm going to guess like 120-ish. What is it? 116. We're going to round that to 2 digits, so 1.2 times 10 to the 2. opposite over adjacent, 20 over 114. We should end up with a small number for theta here as well. What do we get? 10 degrees. Now, I'll show you one more tiny little thing here, okay? Don't lose any sleep over this, but did anybody happen to draw it like this? 20 and 114.64? Anybody do that? That's drawn correctly, isn't it? Look, my vector diagram is drawn head to tail. My resultant vector goes down here. The value of my resultant vector will be the same, 1.2 times 10 to the 2. Theta, though, won't be 10 degrees. Theta would be, anybody want to take a stab at it? What'd you get? Did you draw it like this? To do it like this, your angle shouldn't have been 10. If you draw it like this, your angle should be 80. Well, how can they both be right? They are. How can they both be right? Look, right now, let me describe my position. I'm 2 meters from that wall. I'm 8 meters from that wall. Those both correctly describe my position, right? 2 meters describes it, 8 meters describes it. What's important is my reference point. 2 meters from that wall, 8 meters from that wall. Well, remember I said we really should express a reference point here? 10 meters from what? Or sorry, 10 degrees from what? 80 degrees from what? We'll worry about that later, okay? But know that these are both correct as long as you have a reference point. Okay? As long as you draw that vector diagram head to tail, you're good there. Okay, continue on with number 9, and if you do finish that, go on with number 10. And we may or may not take a look at number 9 today. We for sure will tomorrow if we don't today.